Last time we showed, kind of echoey. I guess it's all right. Last time we showed that you can choose coordinates. In which okay, so we showed last time that you can always choose coordinates at such that at a given point, the metric is just the Minkowski metric up to second order in X corrections. Okay, so space-time can be thought of as being locally flat. This is what we mean by locally flat. Flat is this guy, has no second derivatives. And these second derivatives we call the curvature. Okay, so in the next lecture, we'll be developing this idea of a curved space-time, where the curvature is described by these second derivatives. So before doing that, let us step back a little bit and just discuss general properties of tensors under general coordinate transformations. Okay, so we've already discussed special relativity, where we required that everything be described as a tensor under Lorentz transformations. But when we do general relativity, we want everything to be a tensor under general coordinate transformations. So an example would be a scalar, some quantity with no indices, and the transformation of a scalar is just that the value of the scalar at a given point is equal to its value at the same point in the old coordinate system. Okay, so you should picture it like this. Here's your curved space with the metric G. There is some point P. In the coordinate system X, so let's draw two coordinate systems. Okay, so this will be one of them. This will be X. So we describe the point P using some particular coordinates, the X coordinates, but if I come along and change coordinates to X prime, then of course it's true that X prime, the coordinates of P in the coordinate system X prime is just equal to this function of the old coordinates and the coordinate values of the point P in the old coordinates. Okay, so it's just important to realize that the point may be at some particular value like 1, 2, 3, 4 or whatever in these coordinates, but in these coordinates some completely different value. X prime is 3, 4, 5, 6. And so what you require is that a scalar field takes the same value because X and X prime refer to the same point. Okay, so we have phi prime of XP prime is phi of XP. Okay, so that's a scalar, the scalar transformation law. Likewise, we have vectors. And here we have two kinds. The index can be up or down. And v mu prime etc. Okay, so the rule is there's always one of these Jacobian matrices for every index, and it's dx prime dx if the index is up, it's dx prime if the index is down, and so on. So the number of upstairs indices, and upstairs indices are called contravariant indices. And the number of downstairs or covariant indices define the type of tensor. For example, T mu nu lambda rho sigma equals tensor of type 2, 3. Two upstairs, three downstairs indices, and so these numbers just describe how many Jacobian matrices you need and how many inverse Jacobian matrices you need to describe the transformation law. So the metric, what kind of tensor is the metric? To 0. Okay. Sorry, 0, 2. 0, 2. I get 0. And the inverse metric is 2, 0. Now, how do we get tensors from tensors? Okay, so if we have a bunch of tensors and we want to make some other tensors, how do we do that? Well, there are several operations we can use. We can add them. And so if two tensors are a tensor, are tensors of the same type, then their sum is, so if T mu nu plus S mu nu is a tensor M mu nu of the same type. Right? That's obvious that if I prime everything, I need the right Jacobian matrices in front of these two guys, and those are going to be exactly the right ones to transform M. So you can add tensors to get other tensors. You can multiply them. So I can calculate, for example, T mu nu S alpha rho. That's a perfectly good tensor, right? That's a tensor M mu nu alpha rho of type 2, 2. You can contract And so contract is just an example of multiplying where I choose to sum over these indices. So T mu nu S alpha S nu rho. So that's just multiplying them and summing over the index nu. And so that's a tensor M mu rho of type 1, 1. Now, there's another operation you can do, which is to differentiate tensors, because we know that d by dx mu, or partial derivative, is a vector. So let's try to differentiate a tensor. Because we know that d by dx prime mu is dx alpha dx prime mu d by dx alpha. Okay, partial derivatives transform as a tensor of type 0, 1. So you might be tempted to write down this. And obviously all the equations of physics are differential equations. And so that's the very first thing you want to do if you want to write down some equations for physics using, actually almost all the equations of classical physics are differential equations. The equations of quantum physics are better thought of as integral equations. But for classical physics, you want to differentiate things, see how they evolve in time and space. And so you might be tempted, for example, to take your phi of x, right, and differentiate it. And so the question is that a vector? Is that a tensor? Let's say we define v mu to equal the gradient, the foregradient of phi. Is that a tensor? Doubtful? Well, how do we check? We write down v mu prime, which is d phi prime of x prime, just prime everything, right? And then we know phi prime of x prime is phi of x, and we know d by dx prime is dx alpha dx prime mu d by dx alpha. Okay, so yes, it's a tensor. This is exactly the right transformation law. So v mu prime, so this equals v equals dx alpha dx prime mu v alpha. So indeed, it's a tensor of type 0, 1. Okay, so having made a tensor like this, let's make another tensor. Let's imagine I have some vector. Let me call it something else, just so you don't confuse it with this. Let's say we have b mu nu, d mu a nu, where a nu is a vector, a tensor of type 0, 1. So the question is that a tensor of type 0, 2? Okay, now something goes wrong. Can you tell me what it is? Let's try it again. B mu nu prime is d prime mu a nu prime. But now this has a Jacobian matrix, right? So I get d mu prime of dx prime mu alpha a alpha. That's the transformation of A. Okay, and so what I'm going to get, when this term, of course, differentiates the A, and that will give me the right kind of term, because this will give me dx alpha dx prime nu d mu, well, I'm going to differentiate A with respect to x prime. Okay, so how do I do that? Well, A is a function of x. So I write the derivative with respect to x prime as the Jacobian times d by dx, right? So this gives me dx beta dx prime mu d beta a alpha. So that's a good term. That's exactly right. So differentiating the A gives me exactly the right transformation for a tensor of type 0, 2. But the problem is I've got to differentiate this guy as well. Okay, so I get an extra piece. So I get d2x alpha dx prime mu dx prime nu a alpha. That's nothing like a tensor transformation law, so that's bad. Okay, so you cannot differentiate a tensor with non-zero number of indices and get another tensor. That's quite bad, because it means you cannot write differential equations involving tensors with a non-zero number of indices without some further correction. So B mu nu prime is not a tensor. Is not a tensor. Okay, so again, this is something Riemann encountered, that it's not so easy to define tensor differential equations in this more general setting. And so you need a fix. And the fix is called the connection. So we redefine the derivative as follows. So the idea is to change your definition of derivative. We're not going to use partial derivative. It's not a good operator. It needs a correction. And we're going to redefine the derivative so that I'll first do it for a vector, d mu a nu. This is the covariant derivative. It's covariant because it's got one downstairs index. The covariant derivative of some vector A, by definition, is the partial derivative of A. By the way, I've slipped into this notation of not bothering to write the x. Right? d mu is just d by dx mu. I hope that's clear. And so the meaning should be clear of all these things. You see, we've got a nasty extra term here, so the idea is subtract it off. So we define something like this. Okay, so this is an extra piece, which gamma is the connection. Okay, so gamma is the connection, and its role in life is to make the derivative into a tensor. Okay, so actually gamma cannot be a tensor because it's trying to correct a term that isn't a tensor. And its whole point of gamma is to make the sum of these two terms a tensor. Okay, so the transformation law of gamma, so by definition, sounds like a terrible fix, doesn't it? Didn't work, so I just introduced something to fix it. But we'll see that there's a whole string of consistency conditions which nicely fix what gamma is. Okay, so by definition, gamma prime nu alpha mu, by definition, gamma does not transform as a tensor. It's not a tensor. It transforms using two pieces. First of all, the first piece is exactly the tensor piece, so that would be dx prime nu dx delta gamma delta, let's say lambda sigma, and then these two downstairs indices transform with x prime alpha d by d x prime mu x lambda x sigma. Okay, so that's the normal tensor transformation law. But we want to add to this something involving the second derivatives of the transformation, and want the something to exactly cancel that term. And so the right transformation turns out to be x prime nu dx rho d2x rho dx prime alpha dx prime mu. Okay, and I picked the minus sign exactly so this will cancel that term. Let's just check that. So we've already transformed this term. And so basically this term gave us a tensor plus an extra bad piece. So this term gives us d2 x alpha dx prime mu dx prime nu a alpha. Okay, so tensor plus tensor term plus this guy. And this term is going to give us the tensor term. I've only transformed gamma, but A transforms as a vector anyway. So the combination, the tensor terms are all going to be right. Okay, there's an extra term, which is minus that. Dx prime, now let's see, I forgot the indices. Oh, I need to redefine all the indices. Dx prime lambda, dx alpha, d2x alpha, dx prime nu, dx prime mu. Okay, I just relabeled all these indices. And then the A transforms according to dx prime lambda, x beta a beta, right? And what happens, you notice this is, I've got the Jacobian and the inverse Jacobian contracted on the lambda, right? So we have dx prime lambda, dx alpha, dx, it should be in, yeah, sorry, dx beta, dx prime lambda. Well, that's just delta alpha beta, because that's the derivative of x beta with respect to x alpha. Right? X is a function of x prime. So if I differentiate x with respect to x prime and then x prime with respect to x, I'm just differentiating x with respect to itself. That just gives me a delta. So this term here the delta alpha beta changes this index, makes these two indices equal. So I get exactly minus d2x beta dx prime mu dx prime nu a beta. And that cancels this. Okay, so any questions about that? I introduced some weird object, not a tensor. I just defined it to have this nasty transformation law, but I defined the nastiness exactly to cancel the other nastiness. Okay? Sounds like a terrible cheat. In fact, in gauge theories, in field theory, you do exactly the same thing. Okay? The point is, in a gauge theory, so you have the wave function in quantum mechanics, and you would like invariance under local phasing, local rephasing, where theta is a function, any function of space-time. And then, of course, you find that the derivative of phi goes to the derivative of this guy equals e to the I theta of d mu plus I d mu theta phi. That's the bad term. It means that physics is not locally invariant under redefining phases. And so what you do is you change this to covariant derivative, which by definition is d mu plus I a mu. And then you define the a mu prime. So this is psi prime. A mu prime is a mu minus d mu theta, and it cancels the bad term. So that's the transformation law. In fact, you know, we did this we noticed this was a symmetry of special relativity. We changed A in this way, the field strength was not changed. This is a redundancy in the gauge potential. In the same way, in general relativity, we have a redundancy in the coordinates. We have a connection. So A is the connection in gauge theory. Gamma lambda mu nu is the connection in GR. Neither of them are particularly physical things. What is physical in the gauge theory is the field strength. Even that is not very physical in non-abelian gauge theories. You have to do a little bit more. But in general relativity, gamma is not physical. You go to this curvature, the Riemann curvature. Yes?
So if those things cancel out, it's just the derivatives equal to 0?
No, sorry. Sorry, wasn't clear. So we defined the derivative this way, the new derivative. It follows that d mu a nu prime, right, which is d mu prime a nu prime. It means just prime everything. This is equal to dx prime dx prime alpha beta d alpha a beta, right? So this is a tensor of type 0, 2. That's what it means. Because remember, all the tensor terms I just ignored because they're all sort of obvious. They all do the obvious things, but they all do the right things. The only point all I'm showing here is the bad terms all cancel if you define the connection this way.
How do people come up with this stuff?
Riemann.
How can you find that? Did he just like try for 10 weeks until something canceled?
Yeah. But it'll be a little bit. This is not the answer. This is at this point just a fix. You still have to understand what the hell is this thing. We don't know what it is, and we're going to determine what this is in terms of first derivatives of the metric. You remember the first derivatives of things are a little bit flaky anyway because you can remove them with a coordinate transformation. This thing is a bit flaky, the gamma, and we're actually going to determine the gamma in terms of the first derivatives of the metric. But at this stage, gamma is not determined. It's just something which transforms in this strange way. That's what a connection is.
Why is it not a tensor?
Sorry?
Why is it not a tensor?
Because it has this bad term. This is good. This is a tensor transformation law, just using the Jacobian and the inverse Jacobian. But gamma transforms, by definition, involving second derivatives of the coordinates. It's just a bad term. But you need that bad term in order to make the covariant derivative a tensor. This was not a tensor, so you've got to correct for it. So think about gamma as a correction instead of a connection. It's really there just to correct the derivative. But yeah, as you say, it's actually pretty mind-blowing to think of some PhD student in 1820 or whenever it was, fiddling around with this. I mean, at that time, even partial derivatives were not really very well understood. Certainly physicists didn't know about partial derivatives. It was only in Maxwell developed the theory of partial derivatives. Okay, so Riemann was pretty far ahead of his time. And then, you know, poor Riemann. I mean, Riemann died and never knew that the world is described by this. Okay, so let us now fix gamma. So what is gamma? It's still very mysterious. But before I do that, we've only defined the covariant derivative of a tensor type 0, 1, right? Vector with downstairs indices. What about this? Right? Let me just be difficult and define the derivative of something with an upstairs index. Well, it's pretty clear I get the same problem, right? It's just that I'm going to have the inverse Jacobian matrix here for the upstairs index guy. So I'm going to differentiate that. I'll get another bad term. Okay? So this time it turns out you get a different bad term. So again, d mu, ordinary derivative of v nu, is not a tensor. So we introduce a gamma correction. And I'll just tell you the answer first and then justify it. So we define d mu v nu to be equal to d mu v nu. And this time you have to put a plus. Gamma. Turns out the same gamma does the job of correcting. You don't need a new gamma. And you line up the indices in a slightly different way. So the derivative index always comes on the bottom. And my convention is always to write it second in gamma. When you read different books and review articles, you'll find everyone has different conventions. 10 physicists have 10 conventions, which is very annoying. But we're not engineers. So no one's using this to build bridges. So we don't have to be consistent. But it's still annoying that we can't reach agreement of what the right convention is. But anyway, I'm going to do it this way, and I'll try to be consistent to keep the derivative index second. You see, that's what I did over there. The derivative index is the second one downstairs on the gamma. And then once you make that choice, everything else is fixed because you need a downstairs index, which is the nu. So I put that on the gamma, and I contract the upstairs index of the gamma. I've got to get rid of it, so all I can do is contract it with the A. So here I have a different problem. I've got an upstairs index, and so I use the other downstairs indices on the gamma to contract the V. So that at least looks like it has sensible indices. And this turns out to be a tensor of type 1, 1. Okay, so let me just show you how that works and why I need the plus sign. To see that, let's go back to that bad term in gamma. Let's go back to this bad term in gamma. You see, the structure of it is pretty logical because gamma is something primed. Its indices should be primed. And here the free indices are on the x prime, right? So it's just dx prime, dx prime, dx prime. These are the free indices. The x is the contracted guy. Okay, so it sort of has this tensorial character, even though it's not a tensor, but the primed indices are the free ones. When I consider a vector with a upstairs index, it goes with the inverse Jacobian matrix, right? So instead of, I'll have dx prime dx instead of dx dx prime. So it's useful to try to re-express this in terms of dx prime. This is d2x dx prime squared. It's useful to re-express this in terms of dx prime. I'll just write down the answer and then, well, I may not get the indices right. Yeah, I want to re-express in terms of d2x prime dx dx. You see, this term was canceling the d2x dx prime squared. What I need in the other case is d2x prime dx squared. It's clearly related in some way. How is it related? So the way you relate it is realizing this is kind of the derivative of this identity, right? If I just dropped one of the derivatives there, I would have this. Yes. I dropped the mu derivative. So I have this quantity. Now what's that quantity? This is primed. What is this quantity? This index contracts with that, so it's dx prime dx prime. What's dx prime dx prime? Pardon? Delta, exactly. So this is delta nu alpha, so that's really a simple thing. And this is basically its derivative, except I've forgotten to differentiate this guy. So what that means is I can get an identity out of here. If I differentiate this with respect to mu, right, then this is 0, because delta is just a constant, so it doesn't depend on it. So this is 0. So now we have our identity. And again, this is a trick which we use in GR all the time, is differentiate identities to get other identities. And so here what I've got is d2, let's do this one first, because this is a d by dx prime. So dx prime, let's do that one first. dx, d2x rho, dx prime mu, dx prime alpha, and then with this guy, dx rho. That's the first term. The second term, now here I've got to differentiate d by dx of something. So I should think about x prime as a function of x, but that means this d by dx prime I should re-express in terms of d by dx. So I write it as dx dx prime mu, x alpha, and then d by dx alpha of this, which is basically d2 x prime nu dx rho dx rho dx prime alpha. Okay? So yeah, you do get headaches from doing a lot of these calculations. But I can assure you, once you do enough of them, you'll get happy with them, I hope. All of this is 0, because the right-hand side is 0. So that means we've now succeeded. We've expressed this derivative, d2x dx prime squared, in terms of d2x prime dx squared. Okay? And so using that, the bad term in the transformation of gamma, so this guy over here, so dx prime nu d2x rho dx rho dx prime alpha dx prime mu is equal to minus d2x prime nu dx gamma dx rho dx gamma dx rho dx prime alpha dx prime nu. Okay, so this bad term in the transformation of gamma is related to the bad term you will get in when you take the derivative of an upstairs index thing. And here's the minus sign, with this minus sign. Okay, so using this identity, I hope it's plausible that defining the downstairs derivative in this way also gives you a tensor. The bad terms will cancel. And to demonstrate that, you need to use this identity up there. I'm not going to go through it in detail. But I've showed you there's a minus sign, and it's that minus sign that accounts for this minus sign. Okay, so that's nice, and that's what Riemann did. And furthermore, having corrected the derivative for downstairs index objects and or with one index and upstairs with one index, it's not difficult to do it in general. So in general, if A alpha beta dot 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 is a tensor, and the dots here just indicate any number of indices. Let me keep them ordered. So some number of upstairs indices and some number of downstairs indices. Disadvantage of chalk. Alpha, beta, let's say gamma, delta, is a tensor, right, with any number of upstairs and downstairs indices, then the covariant derivative of it is defined to be the ordinary derivative and then what should I do? How do you think I correct it? How do I add the connection to this formula? I'm going to use the connection to ensure that this is a tensor. Right? Now, it should be pretty clear that every time I have an upstairs indices, I have a certain Jacobian, and I differentiate and I get a bad term. Every time I have a downstairs, I have the inverse Jacobian, I differentiate and get a bad term. So I get a number of bad terms just equal to the number of indices. Each one of them I've got to cancel. The bad terms from the upstairs I cancel with the plus gamma, the bad terms from the downstairs with the minus gamma. And so this is the general rule. And so the upstairs indices, we always do the same. So the derivative index comes last, and it's at the bottom. The gamma basically takes that upstairs index, right, which was alpha, and corrects it. So it contracts with the upstairs index and puts it back. And likewise, the next term would be gamma beta lambda mu. This time we leave the alpha index alone, and we contract the beta index and put it up. Okay, so I guess I should have put these betas here. Delta. So every time you use an upstairs index, you put a gamma, and every time you have a downstairs index, you put a minus gamma. And this time again, the order is obvious. You put the derivative index last on the gamma. I leave all the other indices alone. I contract the downstairs index and put it here, right, etc. Okay, so that's the covariant derivative. Big question, what is gamma? Okay. What equation should determine gamma? We know what kind of thing it is, but how do we determine it? It's not a tensor. It's a little bit of a flaky object. How do we determine? Well, the first point to make, the antisymmetric part of gamma, which, remember, we defined the antisymmetric part to be this, gamma right? The antisymmetric part of a tensor is just obtained by taking the tensor and flipping the indices and putting a minus sign. Actually, this is a tensor. And you can see that because the bad term is symmetrical under the lower two indices. The bad term is symmetric. Bad term in the transformation of gamma is symmetric under alpha goes to beta. Right? Why is that? Because you look at the bad term, it's up there. It's the second term. It's symmetric under alpha and mu, which are the lower two indices. So I take gamma alpha mu minus gamma mu alpha, that bad term cancels. So this is a tensor. All right, so that we're going to give it a name because it is a tensor, deserves a name. We call this the torsion. T lambda alpha beta. Tensor with three indices, antisymmetric under the lower two. The simplest assumption you could make in constructing these derivatives would be T lambda alpha beta equals 0. Okay, because that's really a tensor. So I've written down a meaningful equation. The tensor, the torsion is 0. It's obvious, though very, very powerful fact, but an obvious fact, that if a tensor, so obvious but powerful theorem, which we'll use actually many times, theorem, if a tensor is 0 in one coordinate system, then it is 0 in all coordinate systems. Okay, that's an obvious thing because the tensor transforms with the Jacobian matrix. The Jacobian matrix is invertible. So if the tensor times a bunch of Jacobian matrices is 0, then the tensor is 0. So that's true. So if the tensor is 0, so if I set the torsion 0 in one coordinate system, it's 0 in all coordinate systems. I could just forget about it. It will never arise. Something which I set 0 in any coordinate system will never come back to bite. Okay? So that's a good equation. And it's the simplest thing you can do. Just throw away the torsion. Right? Now, in fact, when this is what everyone did in general relativity, in general, except for very few people. In the late 1950s, people started. See, general relativity had a very strange history. It was invented in the 1915. Now, a few little tests were done: bending of light, perihelion shift of Mercury. We may discuss that next week. These are completely mind-blowing predictions, which turned out to be true. And then people thought, God, this theory is so difficult. It's very difficult mathematically. It's very difficult to test. And they lost interest. Okay, so it wasn't until the late 1960s that there was a revival of interest. The late 1950s, there was a revival. And on the one hand, you had experimentalists like Ray Weiss starting to think, I want to actually detect gravitational waves. And it essentially took them 50 years, over 40 years at least, to build the devices which finally succeeded. Do you know he's coming to give a colloquium? November 30th? It'd be very exciting. So he's an amazing character. I don't know if any of you saw the LIGO announcement. Did you? In Washington? Did you see it? The webcast? So he was there, and he held up a piece of wire fence. It was very funny. He was demonstrating a gravitational wave with a piece of wire fence, which I think he must have picked up on the, in some junkyard. Anyway, so he'll be here to give the colloquium. But anyway, people lost interest in GR. So on the experimental side, very, very brave people started to get interested in the 60s. On the theoretical side, people started to try to couple this to particle physics. Right? They wanted to reconcile gravity with particle physics. So people like John Wheeler, who was at Princeton, was a theorist, revived all this. And of course, his PhD student was Richard Feynman. And I was very fortunate that Wheeler was, when I was at Princeton, Wheeler was there. I used to drive him home after the colloquia because he wasn't allowed to drive. He was too old. And amazing character, the nicest person you could meet. But he tried to couple general relativity to fundamental physics. And that essentially led Feynman, it actually was that work that led Feynman to formulate QED in the late 50s and path integrals and so on. So a lot came out of that. But when they did all this, have you heard of somebody called Kibble, Tom Kibble? So the Higgs, you've heard of the Higgs. So the person who made Higgs, one of the people who made Higgs realistic, discovered how to do spontaneously broken gauge theories was Tom Kibble. And Tom Kibble, in the early 60s, connected gravity to fermions, Dirac fields. Hadn't really been studied. And when they did that, what happened? The torsion came back. Okay. So it turns out that in some ways of doing gravity, when you put fermions in the sort of simplest way you can do, actually the fermions create this torsion field. And ever since then, off and on, people reintroduce. So it's actually needed in some versions of gravity plus fermions. One of those versions is supergravity. It's not a realistic theory, but it's a very nice mathematical theory. And that needs torsion as well. Okay, so that's just a long diversion to say that some people are interested in torsion. It may be there in the real world, but the simplest option is just to set it 0. If we set it 0, then in a very simple way, we can fix what gamma is. So all that words is just to say one can assume gamma is symmetric. There is no torsion. So if we assume torsion equals 0, then gamma equals gamma, and gamma can be determined from a simple condition, namely, so I want to write down an equation which connects gamma to first derivatives of the metric, right? The first derivatives were the flaky things we could remove with coordinate transformations. Gamma is a flaky thing. I want to connect these two things. All right, what's an equation I could write down which will involve gamma and will involve first derivatives of the metric?
Covariant derivative of the metric.
Say again?
Covariant derivative of the metric.
Exactly. Okay. So let's just write this down, see if this makes sense. Obviously, it involves first derivatives of the metric. Obviously, it involves gamma. Let's see what happens if we set that equal to 0. All right, so this is a kind of appealing idea, that the quantity I use to fix the geometry, the metric, does not itself have a first derivative. Right, so that's basically telling you that if you take the dot product between two vectors at one point, and if those two vectors are constants, the dot product is not going to change, right? So if I take a dot product, G alpha beta U alpha U beta, or V beta, right, so what is this quantity? This is U dot V. If the covariant derivative d mu v alpha, d mu u alpha equals 0, so that's the only sort of meaningful way to say that this is a constant vector, is that its covariant derivative is 0, and d mu v beta is 0. So if these are two constant vectors, then yes, actually I haven't emphasized this, but it is true. If I take the covariant derivative of u dot v, this is a scalar, no indices, right? So this is equal to d mu u dot v. And what I'm arguing is that if the u and the v are constants, ideally I'd like u dot v to be constant. All right, at least that's appealing, that I'd have some geometry in which that was true. So what is this equal to? Well, this is equal to, so this is what I want to emphasize, the covariant derivative obeys the same law as an ordinary derivative, in that if you differentiate a product, it's the sum of derivatives. So this is equal to, so let's just write that out, G alpha beta U alpha V beta. This is equal to equal to d mu g alpha beta times, it's distributive. The covariant derivative is distributive, just like the ordinary derivative, plus g alpha beta d mu u alpha u beta or v beta plus g alpha beta u alpha d mu v beta. So this is a property. Covariant derivative is distributive. That just follows from the definition. If you work these things out, you will see that the connections, you see here, obviously, I'm going to get two gammas with minus signs, because G has two lower indices. Here I'm going to get one gamma with the plus sign, one gamma with a plus sign, and you check these just cancel. So the covariant derivative has the same property as a derivative, that the derivative of a product, covariant derivative of a product is just a sum of the terms where you differentiate each thing. So given that if these terms are 0, and I want this to be 0, because I want the scalar product of two constant vectors to be constant, it follows for arbitrary vectors, this is a v, for arbitrary vectors u and v, it follows this must be 0. So that's an appealing property, that the metric doesn't somehow, doesn't change covariantly across space-time. So this equation is called metricity. I think that's a more modern word. And some brave people like Lee Smolin and Laurent Friedel like to imagine that the metricity is not 0. And then you can try and do experimental tests to see whether this is indeed valid. Okay, so they proposed that the metricity not be 0 in order to create some interesting effects in cosmic ray physics. So far, all the evidence is against those interesting effects, but nevertheless, interesting idea. Okay, so if we impose this metricity equation on the metric, the claim is this fixes gamma. All right, so let's just see that. This is d mu g alpha beta, two downstairs indices, so I've got minus gamma and then another minus gamma. I first use the alpha index, so this is g lambda beta, and then I do the beta index equals 0. That's the equation. Does that equation look a little bit, I want to solve for gamma. Does that equation look a little bit familiar? It's an equation which is symmetrical in two indices, the alpha and the beta, right? So it's symmetrical under alpha changes to beta. These two terms are just related by exchanging alpha and beta. So have we seen an equation like that before? We did last time, remember? We solved for something called L, symmetrical in the two downstairs indices and one. In fact, it's the same equation. So how am I going to solve that equation? It's a limited number of algebraic tricks. Add two more equations, okay? So I leave that to you just because time is running out. But obviously what we do is we what do we do? We cycle the indices, all right? Plus, so basically we're going to do a plus of the same equation. It's like, yeah, let me think. There was a logical way of thinking about this, but let me do it without the indices. Okay. So we add one version, we subtract some version. Okay. This is, by the way, in the printed notes. You may know this. There are some printed notes. They're not properly proofread, I warn you. So I don't guarantee their correctness. But so you add and subtract the same equation, and it turns out lots of terms cancel, and then what we find is that gamma lambda alpha mu is equal to G lambda beta G alpha beta mu plus G mu beta alpha minus G alpha mu beta. Okay, and that is often called this funny symbol, which is the Christoffel symbol. I can do the algebra if you really want me to, but maybe more fun for you to try it. Let me know if you get stuck. And so that's that. With this extra assumption of metricity, which is kind of plausible because you want scalar products to be preserved for vectors which are covariantly constant, with this extra assumption of metricity, gamma is completely determined in terms of first derivatives of the metric. Now, I told you last time, we can always choose coordinates in which these first derivatives are all 0. Okay, so what happens in that coordinate system? In a coordinate system where the metric's first derivatives are 0, what is gamma? 0. The gamma is 0 in the coordinate system where the first derivatives of the metric are 0. Is gamma 0 in all coordinate systems? No, why not? If it was a tensor, it would be. So if a tensor is 0 in one coordinate system, 0 in all coordinate systems. Gamma is not a tensor. No need for gamma to vanish in other coordinate systems. So, okay, so in fact, next time we will see, you will remember that I showed you that in a uniformly accelerating coordinate system, right, a freely moving particle actually accelerates. And that acceleration comes from the gamma. Right? So gamma is the fictitious gravitational force created by a coordinate transformation. That's really what it is. It can be removed by a coordinate transformation, which takes you back to the freely falling system. So locally in any region of space-time, gravity doesn't really exist, doesn't have any influence at all. Everything is special relativity. Gravity can be removed. The only way gravity comes into physics is if you look at regions of space big enough that the curvature of space-time matters. The second derivatives can't be removed and become significant. And that's all described by the Riemann tensor. So next time, having fixed gamma in terms of the metric, next time we're going to fix the Riemann tensor in terms of the gamma. Just like in electrodynamics, A mu is the connection. That's analogous to gamma. And the field strength was a physical thing. That was the electric and magnetic field. So the field strength is analogous to the Riemann tensor in gravity. Okay? And just like the field strength is d mu a mu minus d nu a mu, so Riemann is some kind of anti-symmetrized derivative involving gamma. These are very close parallels. So I hope as you understand the subject, you will, in a way, realize that Maxwell was the one who made the big breakthrough. Right? When Maxwell found how to write the laws of physics as a set of PDEs with this huge symmetry, that was a very, very profound impact. And Einstein was doing nothing more than just doing that for gravity. Okay, so Maxwell's the one who should get all the credit. In fact, Einstein always gave Maxwell the credit for his work. And Maxwell gave all the credit to Faraday. Because Faraday was the experimentalist who, although he had no maths at all, he sort of intuitively realized there are things called fields. And that's where Maxwell got the idea from. I'm sure Faraday would give the credit to somebody else. Not sure who, but any questions?
Where did you use the fact that the torsion is 0?
Why did I use it?
Where?
To get gamma being symmetric. Okay, so in this calculation, if gamma was not symmetric, the terms wouldn't cancel. Remember when we did this calculation for L?
Yeah.
It was very, very important this was symmetric. It was not symmetric, you couldn't solve these equations uniquely for gamma in terms of dg. Okay, so it's the vanishing of the torsion that enables you to express gamma in terms of first derivatives of the metric. Otherwise, it's undetermined. You see, the way to think about it is torsion really is a tensor. It's a new object. You should think about it as a physical field, like an F mu nu or something. If there's some torsion there, there's really some extra physics creating it. There's nothing you can... So the theorem is, if a tensor is 0 in one coordinate system, it's 0 in all coordinate systems. The converse is if it's not 0 in any coordinate system, it's non-zero in all coordinate systems, right? And so it's going to be there to muck up everything you're doing, whichever coordinates you use. So, and that's reflected when you work out these equations. You simply can't express gamma in terms of this alone. Of course, what happens is you can write gamma in terms of this plus torsion terms, plus some extra terms involving the torsion. And then you wonder what fixed those. All right, so you get this framework which has an extra physical field, and you don't yet know what fixes it. In theories with fermions and supergravity and so on, there are other principles which would fix the torsion. But if you just do plain GR, there's nothing stopping you from setting the torsion to 0, and that's the simplest case. So I think torsion is definitely very interesting, but A, there's no evidence for it. And B, the theory without torsion makes perfect sense. So different people take different attitudes. Some particle physicists like to say there's this whole kind of effective field theory dogma, which says that all operators which could be there should be there at some level. Right? That's one. You'll hear these words a boringly infinite number of times. Okay. That philosophy would indicate you should leave the torsion in until you know it's not there. And that's okay. But there's another philosophy which is the opposite, which is to say, let's keep things as simple as possible and not introduce extra fields or couplings until there's evidence for them. And I would have to say the second philosophy is winning right now. So like this idea that everything that can be there should be there at order 1 is losing very, very badly. Nature seems to have lots of conspiracies to keep things simple. And we don't understand those conspiracies yet. So nature is not just some random theory. So I would say we don't really understand why the torsion is 0, but there's no indication for it, and it's totally reasonable at this point just to ignore it. Yeah.
If you happen to get lucky, for example, find a coordinate system where gamma is 0.
Yes.
Doesn't that imply the torsion has to be 0?
Torsion. That's a good.
Because the transformation law for gamma
Yeah, that's a good point. Well, let's see. So there's a bit of a contradiction here, isn't there?
Without assuming...
No, wait a second. This is the statement. Okay, so if you find a coordinate system in which gamma... wait a second.
That's on the local.
It's only at one point.
Yeah, gamma is 0 at 1 point.
At one point. Yeah, so we couldn't always find a coordinate system where gamma is 0 at a particular point. So the torsion is 0 at that point. And that will be, let me think. Yeah. But doesn't that imply that I could always... Yeah, so I guess you're saying the torsion... yeah, it's a good question.
I'm just thinking about what you can learn directly from...
Right.
information you have.
Right. It's a good question. Let me think about it. Any easier questions? Or any harder questions?
If you're in 1D, can you always transform to a flat space globally?
Yes. So in 1D, so what is a 1D metric? It's just a function of x times dx squared. Actually, usually when I call it a metric, what we usually do is write a line element. We think of that as a more physical object than the metric because that is g mu nu dx mu dx nu. So that's the proper distance. That's a physical distance between 2 points separated by dx. Okay, so the line element is this. Now in one dimension, it's just that. The reason this is nice to think about it is, of course, this is invariant under coordinate transformations, right? So this, let's call it ds squared. So ds prime squared in some other coordinate system is g mu nu prime dx prime nu. But of course, this is just dx prime with lower indices, g alpha beta, and then dx. These are transform with the Jacobian, so dx prime. Okay, and then these guys cancel. So the line element is invariant under coordinate transformations. So it's always nicer kind of to think about this quantity. So the statement is that in one dimension, the line element's always of that form. Okay, so what I'd like to do is write it as dx prime squared, because that's the trivial line element. That's flat space in one dimension. So can I do that? Yeah, it's easy because, well, let's imagine this is the square of something, so it's positive. Remember, to do geometry, you always require the metric is invertible, and you fix the number of positive and negative eigenvalues. So if we say this is a metric in 1D, it has one positive eigenvalue, it must be the square. And so all I do here is I say dx prime is equal to f of x dx. I can solve that equation. X prime is integral, right? So it just says in these coordinates, the metric is flat. So in 1D, it's trivial to make the metric flat just by choosing coordinates.
But if your manifold is like one closed circle, doesn't it need to have curvature in some sense?
No, a circle is flat. A circle is flat. Why? Because the metric, let's say theta is the angle on the circle, and we can do it just like we did the two-sphere. We can work out the induced metric on the sphere. It's just d theta squared. And this metric has no curvature. So it has an extrinsic curvature, but not an intrinsic curvature. So if you're completely confined to the circle, you really can't tell. Now, what it does have is a non-trivial topology. You know, if I compare a line, a straight line, going from minus infinity to infinity, well, first of all, that has two ends, which this doesn't have. And secondly, it's infinite. So the circle has a non-trivial topology, but the topology is a totally different property than the geometry. The geometry is always a local property, and it's determined by the metric. And so these two have the same geometry, but different topology. So when you study GR, we're only studying the geometry of space-time, not its topology. As far as we know, the universe could be topologically non-trivial. I could travel over to the other side of the universe and reappear on that side. That's allowed by GR. Okay, so it could be like a torus. You could go around and come back. And so topology and geometry are related, but different things. So certain topologies allow certain geometries. But the geometry does not fix the topology. So 1D is always trivial. You just change coordinates to coordinates in which it's just a line with Euclidean geometry. This is Euclidean geometry. 2D, there are various facts, you see. So in 2D, there's another theorem which is analogous to this. Remember, in 2D, I told you the Riemann tensor only has one component. Right? We proved that. We proved that we can set all second derivatives of the metric to 0 except for one in 2D. This relates to the fact that in 2D, you can always choose coordinates. So it can always choose coordinates in which g mu nu is equal to some function of x times eta mu nu, assuming Lorentzian. If it has one negative and one positive eigenvalue, you can always choose coordinates, and this is called conformally flat. So 2D geometry is always conformally flat. The only sort of interesting description of the geometry is a single function of x, which is just the overall stretching of space. Okay, there are no interesting angular deformations in 2D geometry. It's all just a stretching. And so that's, as you know, people study conformal field theories and all that, and they work most beautifully in 2D, and that's related to this fact. All 2D spaces are conformally flat. 1D spaces are all flat, 2D are conformally flat. 3D, a little bit more comes in, but no gravitational waves. There are no gravitational waves in 3D. Only when you get to 4D, you get gravitational waves possible. And the geometry becomes, much more interesting. Any other questions?
Why does the U and V, the dot product U and V has to be 0?
Oh, I'm just saying, okay.
It's an assumption?
It's assumption. So if I want U dot V to be 0 when d mu U alpha equals d mu V beta equals 0. So if I have some vectors which are covariantly constant in space-time, and if I would like these conditions to imply this, then I must have that the metric derivative is 0. Okay, so it's only an assumption. It's a simplifying assumption. But the other statement is, if you have torsion around and you have two vectors which are covariantly constant, physically some examples would be the spin of a particle, particles following some trajectory through space-time, and its spin is a half and it's constant. Now, if you have another particle with where a spin is some constant vector, you have another particle and they're moving along, and if you want that dot product not to change, then you better not have any torsion. The torsion is going to change that inner product. It's again saying it's really something physical. It's a quantity which could exist, but it can be set to 0, and that is the simplest theory, is no torsion.
Following on from the
previous question, can you give an example of curved space in 1D then?
No, there's no curved space in 1D. You can set all the, you can always just do this in 1D. So give me any metric you like in 1D. Give me a metric. I mean, I could have done it this way. I could say G11 of x is f squared of x. And then all I do is a coordinate transformation. G11 prime of x prime, right? It's just dx prime, dx prime of this, f squared of x. And all I have to do is choose the dx prime. So I just choose dx prime to equal to 1 over f of x. And that's just the same as this equation. That dx prime. Partial derivative is an ordinary derivative in one dimension. So dx prime is f of x dx. So in other words, it's these factors that allow you to just remove any non-trivial x dependence in 1D. But in higher dimensions, you can't. Any other questions? Think you need a break? All right, see you tomorrow.